To avoid revocation of my license as a mathematician, I occasionally need to do public service announcements. So, in order to keep my membership up to date, we need to introduce a surprising connection between the whole numbers and calculus. For our whole numbers n, we define 0 factorial to be 1 and n factorial to be the product of the descending sequence of whole numbers. We could define a factorial function, but could we evaluate this if n is a fraction or a negative number? No, but maybe. Let's consider this integral. One of the interesting features of mathematics is sometimes a harder problem is actually easier. So instead of having a specific exponent, let's consider what happens if we try this integral with an arbitrary exponent. We can use integration by parts, and so this integral is and note that when we apply this, we get something that looks very much like our original integrand, but the exponent on x has decreased by 1. And this is sometimes referred to as a reduction formula because we take an integral of one form and we reproduce a very similar looking integral with maybe some other things attached to it. And so the integral involving x cubed, well, that's really 3 times the integral involving x squared. But wait, there's more. The integral involving x squared, well, that's really 2 times the integral involving x to the first. And then the integral involving x to the first is 1 times the integral involving x to the 0. And, oh, well, I guess we still have to do some work here. We have to evaluate this final integral by hand. Fortunately, that's not too difficult. And notice that this integral with exponent 3 is 3 factorial. Now, factorial isn't well defined if n isn't a whole number, but integrals can use any power on x. And this allows us to define the following. For alpha greater than 0, the gamma function, and this is the Greek capital letter gamma, is defined by this integral. And one thing to note, the exponent on x is actually alpha minus 1. There's a reason for that that'll become apparent in a second. So if we define gamma alpha to be, using integration by parts as before, this exponent alpha minus 1 comes out as a factor, and the exponent drops by 1, but this is now gamma of alpha minus 1. And so that gives us this nice result. If alpha is greater than 0, then gamma of alpha is alpha minus 1 times gamma alpha minus 1. And that's part of the reason that we use the exponent alpha minus 1 is it gives us a nice symmetry to this reduction formula. And that means for whole numbers, gamma of n, well, that's n minus 1 times gamma n minus 1. But gamma n minus 1 is n minus 2, gamma n minus 2, and so on. And if we continue this, we'll eventually arrive at n minus 1 factorial. And notice that if we define n factorial to be gamma of n plus 1, then 0 factorial is gamma of 1, which is just 1. So instead of coming up with some torturous argument of why it makes sense that 0 factorial is 1, we can just compute it directly. Now we could compute gamma of alpha for non-integer values. However, that generally requires numerical approximations or some very advanced mathematical techniques, so we won't today.